Hello everyone and welcome to Lecture 9 of Computer Architecture. Today we're going to talk about sequential logic, and in particular we're going to talk about the fundamental building blocks of sequential logic, which are latches, flip-flops, and we will also talk about registers. So a quick review of what we covered last time. We're still in part 1 of logic design. Last time we continued speaking about building an ALU. We saw how to build support for checking for equality in an ALU, and we said that we implemented equality. We checked if A equals B by checking if A minus B is equal to 0. And the way we did that is by subtracting, using subtraction to get A minus B, and then taking the result of the subtraction and passing that through a NOR gate. And if all the bits were 0, then the NOR gate will return 1. If any of the bits were not 0, then the NOR gate will return 0. And this is how we implemented equality. We also looked at how to detect overflow, and we saw how the cases where we have overflow are either if we're adding two positive numbers and get a negative number, add two negative numbers, get a positive number, or subtract negative from positive and get negative, or subtract positive from negative and get positive. So these cases are impossible arithmetically, and when these cases happen, this is an indication that some overflow occurred in the addition. So the way we implemented overflow was as follows. We looked at the different cases for the last bit of the two inputs and the last bit of the output. And when we had two positive numbers giving us a negative number, in other words, the most significant bit was 0 for the two inputs, but 1 for the output, or vice versa, we detected that there was an overflow. And we used this equation to represent how we can detect overflow, and implementing this equation would take 11 gate inputs. But then we realized that we can actually express it more concisely if we express overflow in terms of C in n minus 1 and C out n minus 1. And this gave us a more concise way to express the condition for overflow and hence a more efficient circuit to detect it. We modified the most significant bit ALU in order for us to have an overflow detection unit in the ALU in order to detect the overflow. This is how we incorporate overflow into our final n-bit ALU. And then finally, we looked at how we can configure our 1-bit ALU, give it different select signals to perform different operations. And we looked at the control signals for each operation. And we also observed that we actually don't need B invert and C and 0 separate, because C and 0 is just equal to B invert. And then finally, we looked at the kind of our final ALU that we had built. Takes two inputs, an operation, produces an output, and also produces 0 and overflow, which are useful in detecting when the output is 0 or when we have overflow in the addition. So that is what we covered last time. Any questions about last time before we move on to today? Okay, if there are no questions, then I'll start talking about latches, flip-flops, and registers. So a while back, we said that there are two general categories of logic blocks: combination logic, where the output depends only on the input, and sequential logic, where the output depends on both the input as well as some values stored inside of the circuit. We started by focusing on combination logic, and today we're going to start talking about sequential logic. So let's get started. If you remember, a while back we spoke about clocks. We said that a computer is driven by a clock, and there's this notion of a clock cycle. The clock ticks up and down, and kind of the distance between two similar edges is called a cycle. We said that kind of a typical way that things happen in a computer is we perform some operations during the cycle, and then on the active edge of the cycle, we do some update to the data that's stored inside the circuit. So we compute, and then we update, and then compute, and then we update. We call this transition between two values of the clock a clock edge. So here this is a rising edge, here this is a falling edge, here this is a rising edge, here this is a falling edge. So the rising edge is where the transition happens from 0 to 1, and the falling edge is where the transition happens from 1 to 0. Edge-triggered clocking is a methodology where the update happens either on the rising edge or on the falling edge. And whichever edge the updates take place on, this is called the active edge. So in this diagram over here, what's the active edge? Is it the rising edge or the falling edge? So in this diagram, the active edge is the rising edge, because here we're doing the computations in between two rising edges, and we update the state on the rising edge. So in this diagram over here, the active edge is the rising edge. And you can have other clocking methodologies where the active edge is the falling edge, okay? All right, so given that we have this edge-triggered methodology clocking, a state element, so in edge-triggered clocking, a state element, which is the fundamental building block of sequential logic circuits, a state element is a circuit component whose contents only change on the active edge, okay? So a state element is this logic block where the data that's the content that's the state that's stored inside the logic block will only change on the active clock edge. So for example, when we build sequential logic circuits, we usually have kind of a state element and then some combinational logic and then some other state element. And what happens is that during the duration of the clock cycle, the data that's stored in this element will be read over here. This combination logic will perform some operation on the data, compute something with the data, produce a result, and then the result will sit and wait over here. And then once the active edge occurs, that result will be stored inside of the state element. And most likely some other value will be stored inside of this state element. And then on the next clock cycle, this combination logic will start computing on the new value. And then something else later on will start computing on the new value in this state element. Okay, I'll show you an example. So for example, let's say we had this case over here. We had a state element, some combination logic that performs the operation F, and then another state element. So over here we have A sitting here as an input to the state element. However, the state element is not going to update its value to A until we reach the active edge. So in this diagram, we're going to consider that the active edge is the falling edge. When the active edge occurs, so when we have the active edge, the A that was over here will jump in and get stored in the state element and also become the output of this state element. On the other hand, when this active edge occurred, we probably have some changes that are taking place over here, but these changes are not going to affect the state element because the state element holds its value until the next active edge. So now we have a new cycle, and then during the cycle, what happens is this A is going to travel through this combination logic. Oh, so like I said, we're going to update the state on the falling edge, and then this A is going to travel through this combination logic throughout the duration of the clock cycle, and at the output here, we're going to have F of A. And then this F of A is going to sit here at the input of the next state element and wait for what? It's going to wait for the next active edge. When the next active edge, and then meanwhile, whatever was here before has computed some value B, and this B is also going to wait here at the input of this state element until the next active edge. So when the next active edge occurs, what's going to happen is that B is going to become the content of this state element, and F of A is going to become the content here. So let's see that. Again, here we're going to hold the state. And then during the clock period, the signal from here is going to propagate. We're going to get B here. This A is going to propagate through here. We're going to get F of A over here. And then when the next active edge occurs, you'll notice that now the value inside of the state element is B, and the value inside of this state element is F of A. So we're going to update the state of each of the state elements on the falling edge. Now, during the clock cycle, what's going to happen is that whatever was going on back here eventually will update this value. This B is going to travel through this combination logic, and we'll have a new value over here. So here, after the clock cycle, we get C at this input. We're going to get F of B over here. But notice that this state element doesn't change its value, and this state element also doesn't change its value. On the next clock edge, they're going to hold the state throughout the duration of the cycle, and then on the next, and here we're going to get new values that arrive, and then on the next clock edge, now C becomes the new value over here, and also at the output, and F of B becomes the new value over here. and also at the output. So this is kind of an example of how sequential logic works. Any questions about sequential logic? Does anyone have any questions?
Sir?
Yes?
What if an operation takes like 2 cycles, clock cycles?
So we can't have that. If you mean if some combination logic operation takes 2 cycles?
Yes.
So we can't have that. We need to make sure that whatever combination logic we put in between two state elements can complete in 1 cycle. Okay?
Okay.
So if an operation takes 2 cycles, what we have to do is we have to split the combination logic for that operation into 2 parts, do 1 part in 1 cycle, store the intermediate result in a state element, and then do the rest in the next clock cycle.
Okay.
Okay, very good question. All right, so this is how state elements work. Again, we update. So now the question is, how do we build state elements? How can I build a circuit, right? So far we've seen, we take inputs to logic gates, they give us outputs, but how can we use logic gates to actually store data? How can we build a logic block that stores data inside of it and then updates that data on the rising edge? Okay, that's the question that we will try to answer in today's lecture. Okay, so again, I wrote the goal down here. I'm gonna keep it down here for the rest of the lecture. Our goal is we want to hold the state throughout the clock period and update the state on the falling edge. Okay, because here we're considering that the falling edge is the active edge. So let's see how we can do that. In the first example, we're going to look at a configuration of logic gates called a latch. Okay, we're going to start by looking at what a latch is. So here what I've done is I have 2 NOR gates, and the first NOR gate up here has an input B and an output C. The second NOR gate has the output D, has an input A. But then what I've also done is I've taken the output of the first NOR gate and provided that as an input to the second NOR gate. And I've taken the output of the second NOR gate and provided that as an input to the first NOR gate. Okay, so I kind of have this loop backwards in my circuit. Okay, so let's see what that does. Okay, let's see what that does. So let's look at the different cases for what my input could be and what my corresponding output will be. If I set in the circuit, if I set A to 0 and B to 0, well, if I set B to 0, then C is going to be NOR of B and D. So if B is 0, then 0 or D is just going to be D. And then you invert that, that's going to be not D. So here C is going to be not D, or the old not D, because D might change after I apply 0, 0, but in this case it won't. Okay, and then if I apply A as 0 over here, then here I'm going to have 0 or, and then the value coming in from here is C, so I'm going to have 0 or C. So 0 or C is going to be C, and then I have a not over here, so D is going to be not C. Okay, so C is going to be the old not D. If I apply 0, 0, then C will be the old not D, and D will be the old not C. Okay, does someone have a question?
Yes, I don't get how do we start. And for the first one to give an output, it needs the output of the second one, and the second one to give an output, it needs the output of the first one. So how do we start?
So right now I'm presuming that there was an output there before. Right now I'm presuming that we had some way to initialize C and D, and and the next inputs we're going to do that. Okay.
Oh, okay.
But for now, assuming that before we set A and B to 0, 0, right? They were set to something else, and C and D had value. What's going to happen when I set A and B to 0, 0 is that that value is going to stick. Okay, because if A and B are 0, 0, D is just going to be. So here, A and B being 0, 0, this will hold the state, and this is partially what we want. We want to be able to hold the value inside of a circuit, so a latch does that. If I set A and B to 0, 1, let's see what happens then. So if A is 0 and B is 1, here if B is 1, then regardless what D is, 1 or whatever D is going to be 1, and then not that is going to be 0. So if I set B to 1, C will be 0. And if I set A to 0, then A will be 0 or C, and I know that C is going to be 0, so 0 or 0 will be 0, and not that will be 1. So in this case, C is going to be 0 and B is going to be 1. So if I set A and B to 0, 1, then C and D will be 0 and 1. So I hope this answers your questions about how we started, how we kind of had initial values.
Yes, thanks.
Yep, you're welcome. So here, setting B to 1 and C to 0 will reset C. Setting B to 1 will set C to 0. So we're going to call B later on, we're going to call it R because it performs a reset, okay, of C. Now let's consider the case where we set A to 1 and B to 0. Well, the opposite's going to happen. If I set A to 1, then 1 or anything is going to be 1 and not that's going to be 0. So D will be 0. And then the D comes over here. We're going to have 0 or B, and B is 0 in this case. So 0 or 0 will be 0, and not that will be 1. So C is going to be 1. So if I set A, B to 1, 0, they will set C to 1 and D to 0. Okay? So here A sets C. So later on, we're going to call A S. All right? And then finally, let's look at the final case. In the final case, if I set A to 1 and B to 1, well, 1 or anything is going to be 1. So C is going to be 0. And A or anything, so if A is 1, then 1 or anything is going to be 1. And in this case, D is going to be 0. So if I set A and B to 1, 1, then C and D will be 0, 0. Okay? And actually, this input here is not interesting to us. So what we're really interested in are these first three. In these first three inputs, one of them will set C and D to 0, 1, one of them will set C and D to 1, 0, and one of them will set C and D to whatever their old value was. Okay? So here we'll notice that for the cases that are interesting, so if we ignore the last row, for the cases that are interesting, D is always not C, right? Because here C is not D, D is not C, here C is the opposite of D, here C is the opposite of D. So it really doesn't make sense for us to have C and D as kind of different values. Instead, what we're going to do is we're going to call C Q, and we're going to call D not Q. Okay? So we're going to call A S because it sets C. We're going to call B R because it resets C, and we're going to call C Q, and D we're going to call it not Q. So this is going to be our new truth table. We have S and R as inputs, and we have Q and not Q as the output. And because the two inputs do a set and a reset, we're going to call this an SR latch. SR because we can do set and reset, and a latch because it latches onto a value. It takes a value, and if you set SR to 0, 0, it will latch onto that value, meaning that it will store that value so that it can be used in the future. Okay? So this is an SR latch. Any questions about SR latches? All right. So if there are no questions, let's move on to the next case. So as a summary before I move on, so SR latches, if we set SR to 0, 0, we will hold the state. If we set SR to 0, 1, we will update the state to 0, the state being Q. And if we hold SR to 1, 0, we will update the state to 1. Okay? Now, this isn't exactly what we want. What we want is we want something to update the state on the falling edge of a clock cycle. But here we're updating the state when SR is 0. So let's see how we can build on this SR latch to reach what we eventually want, which is for the state to update on a falling edge as opposed to update when two inputs are 0, 0. So the next circuit we're going to look at is called a D latch. So what we do with a D latch is as follows. We took this SR latch that we built originally. Okay, we have this SR latch that we originally built. And we're going to put an AND gate. Rather than having S and R, we're going to have two AND gates. And these AND gates are going to have two inputs. The first input is going to be C. and the other input is going to be D. So here C, we're going to pass C to both AND gates, but for D, we're going to pass not D to the first AND gate and D to the second AND gate. Okay, so now let's see, after doing this, how the circuit's going to behave. So in the first case, if I set C to 0, then the input to this AND gate is going to be 0. So regardless of what D is, the output's going to be 0. And if the input to this AND gate is 0, then regardless of what D is, the output's going to be 0. So if I set C to 0, then the input to my latch is going to be 0, 0. And we saw before that if our input to our SR latch was 0, 0, what's the SR latch going to do? It's going to remember the old value. Okay, it's going to hold the old value. So this is exactly what's going to happen. If I set C to 0, then regardless of what D is, I'm just going to hold the old value. So Q is going to continue to be the old Q, and not Q is going to continue to be the old not Q. Okay? Is that clear to everyone? All right, well, the next case is where I set C to 1. So if I set C to 1, then the output of the AND gate is going to depend on D. Okay? Now, if I set C to 1 and D to 0, then here what's going to happen is we're going to have 1 or not 0, which is 1. So sorry, 1 and not 0. So we're going to have 1 and 1. So if I set D to 0, this AND gate is going to give me 1. And this AND gate is going to give me 1 and 0, which is 0. So I'm going to have a 1 up here and a 0 up here. And we know that when we set our inputs here to 1 and here to 0, what's going to happen is we're going to get a 0 up here and a 1 up here, right? That's how the SR latch behave. If I give it a 0 down here and a 1 up here, then we're going to have a 0 up here and a 1 down here. Okay? On the other hand, if I set C to 1 and D to 1, what's going to happen is I'm going to have 1 and 0 over here. So I'll have a 0 up here. And I'm going to have a 1 and 1 down here. So I'm going to have a 1 down here. So when I put 1 down here and 0 down here, this is like having a set operation. So in this case, Q is going to be 1 and not Q is going to be 0. So here, setting C to 1 and D to 0 will give me 0, 1. And setting C to 1 and D to 1 will give me a 1, 0. So in other words, when C is 0, we're going to hold the old value. When C is 1, what's going to happen to Q? What's Q going to be equal to? Q is going to be equal to D, right? Q will be equal to D. And this is why we call this a D latch. It's called a D latch because we have C, which is like our control signal. If it's 0, we just remember our state. And then if it's 1, we update our state to become equal to D, whatever value we gave. Okay, so here when C is 1, Q is equal to D. So I'm going to change this truth table to look like this, right? When C is 1, Q is equal to D, and not Q is equal to not D. Okay, so now what we have is a circuit that holds its state when C is 0 and updates its state to D when C is 1. And you can think of C as a clock, right? I called it C on purpose to represent a clock, right? So here what we have is a circuit that will update state when the clock is 1 and will hold state when the clock is 0. Now, is this exactly what we're looking for? It's a step closer to what we're looking for, but it's not exactly what we're looking for. We're looking for a circuit that will hold its state when on the falling edge. So it'll hold its state when we transition from 1 to 0. But what we have now is a circuit that will hold its state when the clock is 1 and update its state when the clock is 0. So let's see how we can build on this circuit to reach the circuit that we eventually want, which is a circuit that will update its state only when we transition from 1 to 0. Before we do that, any questions about D-latch? Is the D-latch clear to everyone? All right, great. Let's move on. So what we're going to do is we're going to create something called a D flip-flop. And a D flip-flop, the way we're going to create a flip-flop is by connecting two latches to each other. So we're going to take two D latches, connect them to each other in this way. So the output of one is going to be the input of the other. And we're going to connect them to the same clock, but instead what we're going to do is we're going to invert this clock before it goes into the next latch. So here we're going to pass in C as the C for this D latch, but we're going to pass in not C as the C for the next D latch. Okay? So now let's see what the circuit does. What the circuit is going to do, and I'll show you an example. What the circuit is going to do is when C is 0, right? Remember, when the C is 0, what's going to happen is this first latch is going to hold its state. And when C is 0, that means here we're going to have 1, which means that this latch is going to pass its state through. It's going to update its state. On the other hand, when C is 1, the first latch is going to update its state, whereas the second latch is going to hold its state. Okay? So because we have this inverted over here, when C is 0 here, we're going to hold here and update here because C will be 1. And when C is 1, then this here we're going to update over here, but we're going to hold over here. Okay? So let's see an example of that. So let's say we have this initial circuit over here. Initially, the value in this latch at the output of this latch is A, right? So when the clock is 0, like this, what's going to happen is my first latch is going to hold its old value. So I previously had A over here. It's going to continue to be A. But when the clock is 0, the input here is going to be 1. So my second latch is going to update its value. So the A that I provided as the input will also become the state and the output. Okay? Okay, great. So next what I'm going to do is I'm going to pass an input D over here. Okay, so sorry, I'm going to pass an input at D over here, and it's going to be B. So now, because the clock is 0, I have 0 over here. This D latch will hold its old state. So this B that I passed as input will not affect the state of the D latch because C is 0. Okay. Now next, my clock continues, and now my clock switches to 1. So now when my clock is 1, what's going to happen is that now this over here is going to be 1. Right? And this over here is going to be 0. So now my second latch is going to hold its state, which was A. And my first latch is going to update its state. So here B is going to become the new value in this D latch. Okay? So now this D latch updates, the B now can move in through over here. However, because C is 1, this C over here and the second D latch is 0, so B is going to stop here, and this D latch is going to hold its old state. It's not going to update the state. Okay. So now we continue, and now finally we reach the falling edge again. When we reach the falling edge, what's going to happen is that the first latch now is going to have, so when the clock is 0, the first latch is going to be 0. So now the first latch is going to hold the old value, which is B. But the second latch now will update because now C is 1 at the input of the second latch. So now what's going to happen is B is going to propagate through the second latch and become the new state of the second latch. Okay. And this goes on. So here, when C is 0, we're gonna, eventually a new input arrives, which is C, but C is not gonna update this because this latch is gonna be holding because C is 0. And then when C becomes 1, okay. By the way, this C is different from this C. Sorry for the confusion. Here I just mean a new value C. It's not the same as the clock. So here when my clock becomes 1, now this latch will update and this latch will hold. So now the C will travel through this latch, but this latch will keep its old value B, and then it waits until I actually have another falling edge. So here when the clock becomes 1, when the clock becomes 0, now this latch will hold its old value, but then this latch will let the value through. So now I'm going to have C as the output at Q. So what do you notice here? What do we have? When we connected the two D latches in this way and had a clock pass in here and the inverse of the clock pass here, what we're having is a circuit where whenever we have a falling edge, we update the value to a new value. Here, when we have a falling edge, the output's going to become a new value. Okay, so here at the falling edge, the input was orange, was B. So here the output's going to become this orange B. Here, when we have another falling edge, the input was C. So we're going to have a new value at the output, which is C. Okay. Right. So this is exactly what we are looking for. Now we have a circuit called a D flip-flop, which holds the state throughout the clock period and updates the state on the falling edge. Okay, is this clear to everyone? Any questions? I know it's quite a bit to absorb. Usually, kind of the first time you learn about latches and flip-flops, it takes a while to kind of wrap your head around it. But once you get the hang of it, it becomes quite easy. So someone's asking a question. They say it requires that we have the signal occur at both 0 and 1 states of the clock cycle, right? So yeah, that's. I think what you mean is that this input needs to be held at 0 and 1 a little bit, and yes, that's true. Here, you need to have this input holding between 0 and 1, so there's enough time for it to propagate through the latch. Okay, any other questions? All right, if there are no questions, then we'll move on to the next topic for today, which is registers. So a D flip-flop essentially acts as a 1-bit data storage cell, right? So a D flip-flop essentially stores a value inside of it and updates that value on the active edge of the clock cycle. Now, if I don't want the D flip-flop to update its value, I just want it to keep its old value for multiple cycles, I can just not pass the clock to it. So always kind of keep the clock 0, not let it oscillate at the input of the edge, and we'll see how to at the input of the flip-flop, and we'll see how to do that. But essentially, a D flip-flop acts as a 1-bit storage cell. A register is an array of n flip-flops, and therefore a register acts as an n-bit storage cell. So here, if I take n different flip-flops and kind of connect them, make them act as kind of one unit, and give them all the same clock, you can think of we can think of these n D flip-flops as being one register that stores n bits. Okay, so a register is an n-bit storage cell. That's essentially an array of n flip-flops. Okay, it takes n bits, takes a clock, and gives you n bits as output. So here we're using the bus notation. Okay, so this is what a register is. It stores a circuit that stores an n-bit value, and it's implemented by combining n 1-bit flip-flops. Now, given that we can design a register like this, what we would like to do is we would like to have something called a register file, and a register file is essentially a circuit or kind of a logic block that contains multiple registers. And what we would like to do is we would like to be able to give this register file some register number, right? And it gives us data. And in fact, I'd like to be able to read 2 registers at the same time. So I want to be able to give this register file 2 different register numbers, and it gives me, it reads out the value stored in those registers. So for example, my register file might have 32 different registers, and maybe on some clock cycle, I want to read register 5 and register 8. So I want to be able to give here 5 and 8 in binary, of course. And here I get the value of register 5 and register 8. And similarly, I want to be able to update those registers. So I want to be able to provide here, maybe I want to write a new value to register 6. So I provide here register 6 and the data that I want to store in register 6. And on the clock cycle, what's going to happen is the register 6 is going to be updated with a new value. So this is what a register file does. And what I'd like to do is I'd like to implement a register file using what we've learned so far. Okay, and actually, given what we've learned so far, it should be quite straightforward how to implement a register file, because we already know how to implement registers. So everything else is just has to do with selecting and stuff. Okay, so if I want, let's start with reading. So what I want to do is I have kind of a bunch of registers stored in my register file, and I want to be able to give some number and read the output stored in the register with that number. So that's actually quite simple. All we do is we have, registers. So here I'm going to have, if I have a register file with n registers, I'm going to have a bunch of registers, register 0 to register n-1. Each of these registers is going to be kind of an array of flip-flops. And then here, what I'm going to do is I'm going to have the number of the register I want to read. I'm just going to pass that as a select signal to a multiplexer, right? And the multiplexer is going to select the input from the output of one of the registers and provide that as the read data. So here, if I provide 5 as my input, here what I'm going to do is I'm going to select register 5, and the read data here is going to be the value in register 5. Okay. And similarly, if I want to be able to read 2 registers at the same time, I just have another multiplexer. So here I pass read register number 2. So if I read register 5 and register 7 on the same cycle, I'll pass 5 over here, I'll pass 7 over here, and here 7, this multiplexer will select register 7, and the output value here will be the data stored inside of register 7. Okay, so this is how we can build a register file that we can read from. We have a bunch of registers, 2 multiplexers, and then a register number that selects as the select signal for these multiplexers, and the multiplexer will select the values of one of these registers and provide that as the output data. Okay, any questions about reading from a register file? Is this clear to everyone? Okay, well, the next thing I want to be able to do is I want to be able to also write to these registers. I want to be able to update these registers, or maybe select one register and update that register only, because I don't want, I can support updating multiple registers, but I don't need that, it turns out. I just need to update one of them at each clock cycle. So the next thing we're going to do is we're going to see how we can implement the writing capability in a register file. So here the signals of interest are, we're going to have a write signal that tells us whether or not we want to write, because maybe we don't want to write at all in this clock cycle. And if we want to write, we're going to use this write register number to tell us which register we want to write to, and this write data to tell us the value that we want to write to that register. Okay, so let's see how we can incorporate the writing functionality to our register file. So again, we have these registers, and if you remember, these registers are just arrays of flip-flops. So each register is going to have a clock where the value inside of the register is going to update on the active edge of the clock cycle. And then we're also going to have D, which is the value we want to write to that register. Okay. So the first thing we're going to do is we want to pass the clock to each of these registers. But the problem is, if we just pass the clock directly to these registers, it means that all of these registers are going to update on every clock cycle. But I don't want all the registers to update on every clock cycle. I only want to update one register at a time, and I may not want to update any register at all. So what I'm going to do is I'm going to pass. First of all, obviously, we're going to pass the data that we want to write. We're going to pass that to all the registers. Okay, but we're going to pass the clock through an AND gate. Okay, and I'll show you why an AND gate. But essentially, what I want to do is we don't want to set the clock. We don't want to pass the clock directly to all these registers, because what that's going to do is that's going to make all these registers get updated to the new write data. But I only want to update one of the registers. So I'm going to pass the clock through an AND gate, okay? And I'm also going to pass the write signal to an AND gate. And what this write signal tells me is whether or not I want to write to this register file on a specific clock cycle. So maybe I don't want to write to any of the registers. If I don't want to write to any of the registers, what I'll do is I'll set write to 0. And if I set write to 0, then regardless what the value of the clock is, the output of the AND gate is always going to be 0. So all the registers will hold their old value. None of them will update. Now, if I set write to 1, then the clock will pass through. But I don't want it to pass through to all the registers because I only want to update one of the registers. So I want another signal here as the input to the AND gate to only let one of the AND gates pass that value through, and all the remaining AND gates not pass the value through. So I want the input to be 1 for one of these AND gates corresponding to the register I want to write to, and 0 for the other AND gates for the registers I don't want to write to. Right, exactly. We're going to use a decoder. Exactly. So what we're going to do is we're going to provide the register number, which is going to be in binary, to a decoder. And what's going to happen is, if here for my write register, I give it the value 1, so I want to write to register 1, what's going to happen is the output for this 1 over here is going to be 1, and all the other outputs are going to be 0. So this AND gate is going to receive a 1 over here. All the other AND gates will be 0. So all the other C's will be 0 except for this register. We're going to let the clock pass through. So here, when the decoder gives me 1, and when the write signal is 1, then C will pass through over here and will allow me to write to this register. Okay? Any questions about how we write to a register file? The register file is going to be a very important component when we build a CPU later on, because this register file is going to store all the data that we're going to read from and pass to the ALU, or that we're going to take the result of the ALU and store it back in the register file. Okay, so this is a very important structure in our CPU. It allows us to have multiple places where we can store data, read two pieces of data on the same cycle, and also write a value at the end of that cycle. Okay, any questions? Okay, well, if there are no more questions, then that's all for today. If you'd like to read more about what we covered today, you can refer to sections B.7 and B.8. And that's all for today, and I'll see you next time. Bye, everyone.